Now, the first image from the world's most powerful space telescope, James Webb, is here.
We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system. Now, astronomers have captured that moment live.
The James Webb Space Telescope has once again pushed the boundaries of what humanity can perceive beyond the limits of Earth. And this time, its discovery has left astronomers puzzled in a way few events have. Among the countless objects hurtling through interstellar space, one peculiar traveler, known as 3I Atlas, has suddenly presented a mystery that nobody anticipated. Webb's instruments, trained on the faint, icy body, detected something extraordinary. The interstellar object appeared to have split into two distinct pieces. This was not the kind of behavior expected from an object forged in the chaos of another star system and flung into the void, and its sudden fracturing has raised urgent questions about what forces could be at work in the darkness between the stars. Before we start, smash the like and subscribe buttons for more updates. When 3I Atlas was first spotted, it was classified as only the third confirmed interstellar object observed visiting our solar system, following the groundbreaking detections of 1I/Oumuamua and 2I/Borisov. Each of these visitors has carried with it the fingerprints of alien systems, shaped by environments utterly unlike our own. But unlike the smooth, elongated oddity of Oumuamua or the comet-like Borisov, Atlas always seemed more fragile, less stable, a body carrying volatile materials that suggested a story of constant change. Even so, its sudden split came as a shock. Space is not kind to fragile things. Interstellar space in particular is a graveyard of radiation, extremes of cold and isolation. For 3I Atlas to fracture now, under observation, raises questions that cannot be easily answered by the models astronomers rely upon. The Webb telescope's cameras and spectrographs did more than merely detect a break. They captured the eerie image of two luminous fragments trailing faint halos of dust and gas, their combined shape resembling a celestial wound cut open in the fabric of space. The telescope's infrared sensitivity revealed subtle details. One fragment appeared more ice-rich than the other, with differing surface signatures that hinted at chemical layering within the original body. It was as if Webb had cracked open a cosmic geode, exposing strata that had been hidden since 3I Atlas left its native star system untold millennia ago. The realization that such a split could occur under no obvious external trigger makes the event even more baffling. Scientists are attempting to parse the cause, and each hypothesis seems to deepen the mystery. One idea is that Atlas may have carried internal stresses from its violent ejection out of its home system, stresses that had lain dormant until they suddenly found release. Another suggestion involves volatile ices trapped deep within the body. As sunlight from our star penetrated its surface layers, these ices may have sublimated explosively, exerting pressures that cracked the nucleus apart, but this seems too neat, too convenient given the delicacy of the object's survival through interstellar space and its arrival here. And Webb's data shows no obvious signs of a catastrophic gas release that would explain the timing. Instead, the split happened quietly, almost surgically, as though the object chose to fall into halves without announcing the mechanism. The implications are profound. 3I Atlas is more than just a cometary fragment from another star. It is a sample of alien planetary chemistry delivered directly into our cosmic backyard. By splitting, it has effectively given scientists two opportunities to study what lies beneath its surface. Each fragment may carry pristine material untouched by cosmic rays or solar heating, a window into the earliest days of a system light years away. The event offers astronomers a rare laboratory for testing theories of planet formation, interstellar chemistry, and the survivability of fragile materials over unimaginable timescales. Yet the perplexing nature of the split also carries unsettling undertones. If interstellar objects can fracture spontaneously under circumstances we cannot explain, what does that say about the stability of other wanderers? Could Oumuamua's odd acceleration have been a symptom of similar internal stresses that never resulted in a visible split? Could future visitors break apart unpredictably, scattering fragments through our solar system in ways we cannot predict? Each question that arises reminds researchers how little is truly known about the behavior of material forged in alien suns. Webb's vantage point allows it to see subtleties invisible to ground-based observatories. Its instruments recorded faint emissions around the fragments, a diffuse shroud that suggested a kind of miniature coma, as if the pieces were softly breathing vapor into space. This detail adds a wrinkle to the puzzle, for it suggests sublimation is occurring, but not violently enough to explain the sudden cleaving. Instead, the activity appears secondary, a result of the split rather than its cause. That inversion of cause and effect is perhaps what troubles astronomers most. Their models assume volatility drives fragmentation, yet here it seems the fracture preceded the activity. The sheer improbability of the event has stirred speculation about processes more exotic. Some scientists wonder if 3I Atlas contains structural weaknesses caused by radiation damage during its interstellar journey. Over millions of years, constant bombardment by cosmic rays could alter crystalline structures within its ices, leaving it brittle and prone to breaking under subtle stresses. Others propose the possibility of tidal interactions. Although Atlas has not passed close enough to a major planet for a strong gravitational pull, even minor resonances can, over time, add up to unexpected stresses. None of these explanations fits comfortably, but each reveals how much more complex interstellar bodies may be than the relatively well-behaved comets we know from our own system. There is also the symbolic weight of the event. Humanity has long dreamed of studying materials born under alien suns, but such dreams were bound to the hope of future missions to other star systems. With interstellar objects like 3I Atlas, the cosmos delivers fragments directly into our neighborhood. To have such an object split before our eyes is like receiving a letter from across the stars, sealed and mysterious, only to watch it tear itself open to reveal pages written in a language we have not yet learned to read. The Webb telescope, in this sense, becomes not just an observer but an interpreter of cosmic messages, offering glimpses into stories older and stranger than we imagined. For planetary scientists, the split presents an extraordinary opportunity for comparison. The two fragments may evolve differently over the coming months and years, depending on how sunlight affects their surfaces, how volatiles vent into space, and how dust is released. Observing these differences could provide a living experiment in how interstellar objects weather in our solar environment. It is a chance to see not just a static artifact, but a dynamic process in real time, where the heritage of another star system is reshaped under the influence of ours. Astronomers are already recalculating trajectories for both fragments, tracking how the split will alter their paths. Even slight differences in mass distribution or outgassing behavior could cause the fragments to diverge, slowly drifting apart like siblings charting separate courses. This divergence itself is telling, because it reflects how fragile interstellar bodies are when exposed to the forces of a new solar system. In this sense, the split becomes both a scientific opportunity and a cautionary tale about the fragility of such visitors. If we hope to study them in detail, timing and precision will be everything, for these objects may not remain whole for long. The discovery also underscores the transformative power of the Webb telescope itself. Previous generations of instruments might have detected a brightening, or perhaps a faint increase in dust production. But only Webb's sharp infrared eyes could distinguish the clear separation into two bodies and reveal their contrasting compositions. It is a reminder that our new tools do more than extend our reach. They fundamentally change what is possible to know. Without Webb, 3I Atlas might have gone down in history as just another fleeting visitor, its mysteries locked away forever. With Webb, it becomes a cosmic event that demands explanation, one that challenges assumptions about the very nature of matter traveling between stars. The event invites a kind of philosophical reflection as well. If objects like 3I Atlas can fracture unexpectedly, how many interstellar wanderers have passed through our solar system unseen, fragmenting quietly, leaving no record but dust lost in the solar wind? Our detection of such events may be the rare exception, not the rule. And if so, then every observed fragment is precious, a fleeting chance to piece together the hidden histories of distant worlds. The split becomes not merely a scientific puzzle, but a reminder of the fragility of opportunity itself. The scale of the mystery also pushes at the limits of astrophysical theory. Models of cometary behavior are based overwhelmingly on solar system examples where we can track bodies over centuries and see the patterns repeat. But interstellar objects are outsiders. They come from different chemical environments, different stellar conditions, and different evolutionary histories. Their behaviors will inevitably challenge the frameworks we have built, frameworks that are perhaps too provincial. The fracture of 3I Atlas is a signpost telling us that our models must broaden, must accommodate possibilities that once seemed improbable. In this way, the puzzle is as valuable as any clear answer, for it forces a reimagining of the rules by which cosmic bodies live and die. What makes the event even more captivating is its timing within the arc of exploration. We are only at the dawn of the era of interstellar object detection. Oumuamua was discovered in 2017, Borisov in 2019, and now Atlas adds a third. Each has been stranger than the last, each demanding a rethinking of what we thought we knew. If the trend continues, the universe may have many more surprises in store, and Webb's role as observer will become ever more critical. The split of 3I Atlas, then, is not an isolated oddity, but part of a larger unfolding story, one in which humanity is just beginning to learn the grammar of interstellar visitors. The sight of two alien fragments drifting together across the void carries a strange kind of beauty. There is poetry in the idea that something forged in the chaos of a distant star system has traveled for millions of years only to arrive here, in our time, under our gaze, and reveal itself in a way that leaves us astonished. The Webb telescope, with its golden mirrors and unblinking eye, has captured not just an astronomical phenomenon but a moment of wonder, a reminder that the universe is both more fragile and more surprising than our expectations allow. The split of 3I Atlas is an unsolved riddle written across the heavens, and though the cause remains elusive, the implications are vast. It is an invitation to look deeper, to question more profoundly, and to recognize that even in the silence of interstellar space, the universe still finds ways to speak. The moment scientists confirmed that the James Webb Space Telescope had observed the interstellar object 3I Atlas splitting into two distinct fragments, an entirely new avenue of exploration opened. The event itself was brief in cosmic terms, but its significance stretches far beyond the act of division. It represents an intersection between observational capability and cosmic unpredictability, a reminder that when humanity peers into the universe, what is revealed is often stranger than the most carefully constructed theories. To continue exploring the meaning and implications of this event requires looking at the phenomenon not only through the lens of astronomy, but also through planetary science, astrophysics, chemistry, and the philosophy of exploration. One of the most compelling aspects of the split is the window it offers into the material record of another star system. Until this century, knowledge of planetary formation beyond the solar system came primarily from distant starlight, from watching exoplanets transit across suns hundreds of light years away. That was indirect, statistical knowledge, patterns inferred from shadows. But an object like 3I Atlas is matter itself, tangible and real, an emissary carrying with it the atomic and molecular story of worlds that may never be directly observed. When it fractured into two, scientists were presented with the equivalent of two parallel laboratories. One fragment might retain unaltered interior material, the other a shell of processed outer layers, giving researchers the rare chance to compare surface evolution with deep chemistry. This is akin to cutting open a planetesimal and being able to study its insides while it is still active, still releasing data into the void. There is also the temporal dimension of this event. Atlas has likely been traveling for millions, perhaps billions of years before encountering our solar system. Its fracture, therefore, is not merely an isolated event occurring now, but the culmination of stresses and processes that began in another corner of the galaxy long ago. That continuity emphasizes how space is not static but dynamic, a stage where ancient histories play out in moments visible to us. The break may encode information about its birth environment. Perhaps it formed in a binary star system where gravitational influences stretched and compressed its structure, embedding hidden weaknesses that only now revealed themselves. Observing its split is not just about seeing a fragment of ice and rock fall apart, it is about accessing a fossil record of galactic history. To understand what this means, scientists turn to spectroscopy. The Webb telescope's suite of instruments can analyze light emitted and reflected by both fragments, breaking it into spectra that reveal the fingerprints of elements and compounds. Already, hints suggest a rich diversity of ices, water, carbon monoxide, methane, and perhaps more exotic molecules shaped under alien conditions. But beyond identifying what is present, the split allows comparisons in distribution. Are the two fragments chemically identical, suggesting homogeneity, or are they distinctly layered, pointing to complex accretion histories? These questions matter because they speak to how planetesimals grow in other systems, whether through steady gathering of dust and ice or through more chaotic collisions. Each clue becomes a piece of a broader puzzle of how planetary systems across the galaxy build their building blocks. Yet for all its scientific promise, the split remains shrouded in uncertainty. The mechanics of interstellar fragmentation are poorly understood because there is almost no data to compare. Within our solar system, comets break apart from thermal stresses, tidal forces, or internal pressures, and the patterns of those breaks are reasonably well documented. But 3I Atlas does not fit neatly into these categories. Its trajectory never brought it close enough to any planet or the sun to trigger strong tidal disruption, and the observed gas emissions were not sufficient to suggest a violent outburst. That leaves internal stresses as the leading hypothesis, but those stresses are more mysterious in an object that has wandered in the frigid dark for millions of years. What processes could silently accumulate inside a body exposed only to the diffuse radiation fields of the galaxy? One possibility lies in crystallographic transitions within ices. At extremely low temperatures, water ice can exist in several distinct structures, some metastable, others more ordered. Over time, cosmic ray bombardment could slowly alter these structures, embedding regions of stress. A slight warming upon entering the solar system might then trigger a cascade, leading to structural collapse and fragmentation. This scenario is speculative but tantalizing because it suggests interstellar objects may be ticking clocks, primed to alter their state when they encounter new environments. The Webb telescope's data may hold subtle clues, infrared absorption features indicating unusual phases of ice, that could test such ideas. If true, it would mean that interstellar travelers are not inert relics but evolving entities, their journeys shaping their integrity in ways we have only begun to imagine. Another perspective comes from dynamics. Once Atlas split, the behavior of the fragments became a subject of study in itself. Slight differences in mass distribution and gas emission could alter their trajectories over time, causing them to diverge. Monitoring these paths provides insight into the mechanics of outgassing in low-gravity environments. It is not just about tracking where the fragments go. It is about extracting information on how forces at micro levels play out across astronomical scales. Even tiny jets of vapor can act like thrusters, changing velocities by measurable amounts. By following the divergence of the fragments, scientists can reverse engineer the invisible activity that drives them, creating models that can be applied to future interstellar objects. Beyond the physical sciences, the event holds cultural and symbolic weight. Humanity has always been captivated by celestial phenomena that defy easy explanation, comets once seen as omens, meteors as fiery messengers. The Webb telescope's discovery is part of this long lineage of wonder. But unlike the ancients, modern observers can parse these signs with tools of reason and technology, transforming awe into knowledge. That transformation is itself significant, a reminder of the power of inquiry to turn mystery into understanding. Yet even in an age of advanced telescopes and data analysis, some mysteries persist, and their persistence is what sustains curiosity. The unexplained fracture of 3I Atlas is precisely the kind of enigma that keeps science alive, always reaching for what is beyond current grasp. The implications extend into the future of exploration. Missions have been proposed to intercept interstellar objects, to send spacecraft capable of rendezvousing with these travelers and capturing close-range data. The fracture of 3I Atlas underscores both the urgency and the challenge of such missions. If these objects can change suddenly, splitting into pieces, then mission planning must account for volatility. A probe designed to study a single nucleus might find itself chasing multiple fragments, each with its own trajectory. That unpredictability complicates logistics but also enriches opportunity, since each fragment is a source of unique data. Designing for adaptability may become a key principle of future interstellar missions. Another dimension is astrobiology. While no one seriously expects interstellar objects to harbor life, their chemistry is deeply relevant to questions of habitability. Many theories of life's origins emphasize the role of comets and icy bodies in delivering complex organics to young planets. If 3I Atlas carries such molecules, and if those molecules differ significantly from what we see in solar system comets, it would suggest that the ingredients of prebiotic chemistry are widespread, not confined to a single corner of the galaxy. The split has made it easier to sample these materials indirectly, through telescopic analysis of freshly exposed surfaces. Such observations could expand our understanding of how common the seeds of life may be, offering a broader context for Earth's own biological beginnings. In addition to science, there is the question of narrative. Events like the splitting of 3I Atlas become part of the human story of exploration, woven into how we perceive our place in the cosmos. Webb's golden mirrors, gleaming in the cold of space, acted as witnesses to a drama that unfolded millions of kilometers away, yet resonates with human imagination. To tell the story of 3I Atlas is to tell a story of cosmic fragility and resilience, of how objects can endure unimaginable journeys only to reveal vulnerability at the threshold of discovery. It is also a story of tools and vision, of how a telescope conceived decades ago is now rewriting the script of what is possible to see. Looking further into the implications, the split challenges assumptions about interstellar population statistics. If objects like Atlas can fragment, then the actual number of interstellar fragments passing through our solar system may be far higher than what we detect. Many may be small, dim shards of larger bodies, invisible to our current surveys. The discovery suggests we may be undercounting these visitors by orders of magnitude. Each fragment is a messenger from elsewhere, and the more there are, the richer the opportunities to sample galactic diversity. This realization could motivate new survey strategies, pushing for telescopes optimized not just for large intact objects, but for faint, fast-moving shards. The psychological dimension is worth considering as well. For centuries, the night sky has represented permanence, a stage where stars and planets move in predictable patterns. The sudden split of an interstellar object disrupts that sense of constancy. It reminds us that even at cosmic scales, instability and unpredictability are part of the natural order. There is humility in acknowledging that not everything can be predicted, that even with powerful instruments, the universe retains its capacity to surprise. That humility is not weakness but strength, for it keeps inquiry open-ended and adaptive. It is the recognition that the cosmos is not a solved puzzle, but a living mystery. From another angle, the split of 3I Atlas can be seen as a kind of natural experiment orchestrated by the universe itself. Scientists could not have planned such an event, but now that it has occurred, they can harvest its data with all the precision available. It is as though the cosmos, indifferent yet generous, occasionally provides experiments on scales we could never engineer ourselves. The challenge lies in readiness, having instruments like Webb in place at the right time to capture the fleeting phenomenon. In this sense, the event justifies decades of investment in space telescopes, for it demonstrates that the unexpected is often the most valuable return. There is also the matter of galactic context. If Atlas is the third interstellar object observed, it raises the possibility that such bodies are far more common than once thought. Each detection lowers the threshold of rarity, suggesting that interstellar debris is an ordinary feature of galactic ecosystems. If so, then the processes that launch these bodies, planetary ejections, stellar interactions, gravitational slingshots, are likely ubiquitous. The split of Atlas adds a new layer. Not only are such objects common, but their fates may include fracturing, scattering their material across multiple trajectories. This could enrich the interstellar medium with fragments that later become incorporated into other systems, creating a web of shared matter across the galaxy. The idea that dust and ice from a distant star could eventually seed a newborn planet elsewhere is a reminder of the interconnectedness of cosmic processes. On the methodological side, the event emphasizes the importance of multi-wavelength observation. While Webb's infrared eyes revealed the split in detail, other observatories, radio telescopes, ground-based optical arrays, can provide complementary data. Together, these perspectives build a fuller picture of the fragment's evolution. Coordinated campaigns may reveal shifts in brightness, changes in spectra, or alterations in dust production. Each observation becomes a piece of a mosaic, a collaborative effort across instruments and continents to decode the life of an interstellar traveler. This coordination exemplifies how modern astronomy functions as a global enterprise, pooling resources to chase fleeting phenomena. Another consequence is the effect on theoretical models of galactic dynamics. If interstellar objects frequently split, then their trajectories, lifetimes, and distributions must be recalculated. Fragments may slow more quickly, making them more likely to be captured by stellar systems. Others may be accelerated by outgassing, altering the way they spread through the galaxy. These dynamics feed into models of how material circulates across stellar neighborhoods, influencing everything from planetary formation rates to the chemical enrichment of interstellar clouds. Thus, a single fracture observed by Webb ripples outward into galactic-scale theory. The educational potential of this discovery should not be overlooked. For students and the general public, the idea of an alien object splitting before our eyes is captivating, a story that can ignite curiosity and inspire future scientists. It is one thing to read about exoplanets in textbooks. It is another to imagine shards of another star system passing overhead, visible to human instruments. Such narratives anchor abstract science in concrete events, making the vastness of space feel intimate and immediate. The split of 3I Atlas, then, is not just an academic event, but a cultural milestone, one that may shape how a generation views the cosmos. There is also the comparative perspective with the earlier interstellar objects. Oumuamua puzzled astronomers with its acceleration and elongated shape. Borisov resembled a more conventional comet, but with subtle differences. Atlas, by splitting, adds a new category of anomaly. The progression suggests that each interstellar visitor brings a unique mystery, resisting categorization. Together, they imply that the diversity of interstellar bodies may be as great as or greater than the diversity of planets and comets in our own system. This diversity has profound implications for our understanding of cosmic formation processes, suggesting a richness of outcomes that defies easy generalization. At a deeper level, the event highlights the fragility of cosmic relics. Atlas survived untold ages in interstellar space, yet its undoing came swiftly upon entering the neighborhood of another star. That fragility is a metaphor for many processes in the universe: endurance followed by sudden transformation. Stars live for billions of years but die in dramatic supernovae. Galaxies evolve over eons but can be reshaped by collisions. Atlas embodies this pattern on a smaller scale, reminding us that change is universal, even for bodies that seem eternal. From a forward-looking perspective, the event prompts questions about how humanity might one day interact directly with such objects. If interstellar fragments can be numerous, perhaps missions could be designed to collect material, returning samples of alien chemistry to Earth. The split of Atlas suggests that timing such missions would be challenging, as bodies may alter themselves unpredictably. But it also suggests potential advantages. Freshly exposed surfaces could yield pristine samples unavailable otherwise. The feasibility of such missions remains distant, but the discovery plants the seeds of possibility. The broader implication is that interstellar objects are no longer curiosities but essential components of cosmic understanding. They connect local observations with galactic-scale processes, offering tangible evidence of phenomena otherwise inferred. The Webb telescope's role in revealing the fracture of 3I Atlas cements its place not just as a tool of astronomy, but as a bridge between human curiosity and the unpredictable theater of the cosmos. What the telescope captured is not only a split object, but the opening of a field of study, one that will unfold with each new discovery. The fracture of 3I Atlas, as recorded by the James Webb Space Telescope, does more than perplex the scientific community. It reshapes the boundaries of imagination and extends questions into domains that might not at first glance seem astronomical. The breaking apart of this alien traveler is not just a mechanical event, it is a lens through which deeper issues about cosmic evolution, interstellar exchange, and even the philosophical underpinnings of existence itself can be examined. To continue exploring this discovery, it becomes essential to think across scales, disciplines, and even modes of thought. One of the most underappreciated aspects of interstellar objects is the sheer improbability of their arrival in our solar system. The galaxy is vast beyond comprehension, And yet these fragments find their way to us. For Atlas to appear in Earth's neighborhood, and for Webb to have the sensitivity to track it, the alignment of conditions borders on the miraculous. When it split into two, that improbability doubled into an event so rare that it might not be repeated for centuries. The significance of such improbability is that it challenges the assumptions of cosmic indifference. The universe is not tuned for our convenience, and yet here we are, catching glimpses of alien matter precisely when our technology has matured enough to notice. This coincidence alone makes the split a profound event in the history of human observation. From a geochemical perspective, the split presents questions about the composition of matter across different star systems. In our solar system, the elements and compounds available for planet and comet formation follow patterns tied to the distribution of materials from the sun's birth cloud. But Atlas does not share that heritage. Its isotopic ratios may differ, its organics may follow unfamiliar chains, its ice phases may be stable at pressures and temperatures we rarely encounter. Each fragment is a record of chemistry foreign to us, potentially revealing whether the galaxy operates under universal rules or if each star system is truly unique. If future analysis confirms that Atlas contains molecules found in solar system comets, that points to shared processes across the Milky Way. If instead it reveals wholly novel substances, that discovery could redefine our understanding of how varied planetary nurseries can be. The split also forces astrophysicists to reconsider the survivability of fragile bodies during galactic journeys. For an object to travel through interstellar space, it must endure collisions with dust grains, cosmic radiation, and thermal extremes. The fact that Atlas survived long enough to reach us, but then fractured, raises the possibility that such bodies are perpetually at the edge of instability. They are not robust boulders, but precarious conglomerates, just barely holding together until external conditions push them over the brink. This fragility implies that countless other interstellar objects may disintegrate unseen, leaving only invisible dust to trace their passing. What Webb saw, then, might represent only a rare observable case in a far more common but hidden pattern of cosmic decay. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on 3I Atlas splitting? Natural event or